Guys, so I'm going to try as best as possible. Hopefully you've copied down the notes already. Um, it's the starting a new big topic in statistics. Anyone that's taken a stat class, they kind of know what this stuff is. Unfortunately, boss requires me to be out of the classroom on a day like today, so such is life. So I'm going to try and lay down kind of some understanding on what's going on. As we do more problems in this unit, I would hope some of the topics I'm going to talk about in this video become a little bit more clear. I wouldn't expect kind of like 100% understanding by the end, but you know, it's a start. So the big unit that we're doing now is we're talking about things called confidence intervals. Of the remaining things we have to do this semester, one big topic is confidence intervals. We're going to do a bunch of different confidence intervals. The concepts and how they work are all relatively the same. So it's your first introduction to them. We're going to do like 5 or 6 different types of confidence intervals, so it's a lot of repetition. We'll do the other big topic of the semester later on. So 2 massive topics left to go in AP Stats, then we're done. So let's kind of set the table on how this all is working out. So this first page, I didn't ask you. I mean, you could copy it down if you want. I don't know if it's necessary, but it is trying just to get you an idea of like, okay, where are we going? What's happening? So we've been dealing with these sampling distributions a while. So imagine this picture here is that same poster that I have in the classroom, all those stickers, right? We know every single sticker or every single O is you took a sample of poker chips, so you collected a whole bunch of poker chips, and you found their average. You found their X bar, and you put a sticker where that sample averages was. What we know from the last unit is as long as we follow those assumptions, as long as we follow those rules on how we collect our sample, we know this distribution's shape. We know we're going to be approximately normal, which means z-scores are in place, stuff like that. And we know where this is centered, and we know the spread of the sampling distribution, okay? So we know in general this distribution is going to be lined up. If we're talking about means, mu of x bar is lined up with mu, meaning all of my little x bars is going to be lined up with the population average. So the population average, the average of every single poker chip that was in the box, we know our little sampling distribution is going to be directly lined up with the average of every single poker chip that's in there, which there's well over 1,000, okay? So here's the issue, okay? In general, the last unit is all great and dandy, but in general, we never really know the value of mu, okay? Mu, again, remember, is the population's average. We very rarely know what the population average really is. If you know what an entire population is doing and what it's going to do, I mean, life would be pretty easy on this planet. You would kind of know exactly what was going on. We wouldn't need elections, right? Elections is where people finally decide what they are. But if we just knew, like, all right, we already know everyone's going to vote this way, then we just kind of know. So if you knew what the entire population, what they were doing and how they felt, we'd be done. We'd know everything about the population, game over, okay? So for example, like what if I was super interested in mu, the average of every single student at Pattonville High School? A little bit of a weird question to know, but I don't think anyone knows that information. No one has no clue the average of every single student at Pattonville High School. And if I wanted to figure that out, that's going to take a really long time to know that, okay? So if I don't know what mu is, then I won't know what mu x bar is. The whole sampling distribution problems the last unit kind of falls apart. So the question becomes like, what do we do? Where do we go next? And that's where a confidence interval is. So before I get into this, a confidence interval is the idea of you might not know something about the population. So maybe I really didn't know the average weight of all Pattonville High School students. What a confidence interval is going to do is it's going to attempt to use a sample to predict and pin down some sort of knowledge about the population, okay? So I'm going to use a sample, and from that information, I'm going to take a pretty solid guess at, hey, I believe the population's average is somewhere in this range. Here's the mechanics of kind of what's going on. So we're still going to collect our sample as we've always been doing. We're going to follow the same assumptions before. So the randomization, the 10%, the large sample, large counts. something like that, okay? We're still going to follow our rules. The reason we're going to follow our rules is so we know the shape center spread thing kind of theoretically is in play. And what's going to happen is we're going to collect a single sample, and then we're going to kind of pin down and say, all right, well, it works. Here's the reason why it works, okay? We know if we follow our assumptions, we get this general shape, okay? I have, and you can even look at the poster in the classroom, we have a bunch of stickers centered real tight around my center. We're really close to my center. So if I reached into that box of poker chips and I pulled a sample, there's a pretty strong likelihood, as long as I'm following my assumptions, randomization 10%, large counts, there's a really large chance that I'm going to highlight in blue, my sample maybe falls pretty darn close to the center. These stickers way on the edge, those were super rare. They did not happen very often. More often than not, we had a sticker that was towards the middle, okay? Now here's the deal is, the chance that my sample, my X bar, lands dead on the population average, it could happen, but it's not always gonna happen. So the idea is we make an interval, a range of values that, hey, maybe my sample is centered here, but what I'm gonna create is I'm gonna create a range of values and say, hey, based off my sample, I bet the population is somewhere from this low point to this high point. It doesn't matter if it's close to the low or close to high. We're just gonna say it's somewhere in here. And if we can do that, we have correctly guessed the population's average, and we can do a lot with that, okay? Maybe not so much as knowing average weight of Pattonville High School students, who cares, but you can imagine more important questions. So that's what I was trying to communicate down here. So it's very unlikely that X bar is exactly aligned to Muse, so we're gonna create a range of values to try and predict what it's in. So we get to our second page of notes. I'll go a little bit quick through this page. This is kind of the inner workings of what's going on. As we do problems, I'll touch back on this. So our purpose, the purpose of a confidence interval is we're trying to capture the true population parameter. So we're trying to capture mu or p. And we use the wording true population parameter. True population parameter just means the true value of the population, okay? So we're trying to capture an interval. The analogy that some people use is, imagine you're at like a lake or something, and there is one fish you're trying to catch. If you could capture this one fish, voila, you've achieved what you want to do. What a confidence interval is we're going to throw a net out there. Now, this net isn't going to cover the entire lake. That's just kind of insane, right? We're going to throw this net, and we're hoping it's very calculated that the fish is going to be captured somewhere inside that net. It doesn't matter if we catch the fish on the, very close to the edge of the net, directly in the middle. It doesn't matter where, just we're going to throw a net, and we hope inside of it is the thing we want to know, which is the fish in that analogy, or the true population proportion. So, parameter. So here's the makeup of the general equation. You're going to have a statistic. You're going to add or subtract your critical value times your standard error of the statistic. What this back part is, the critical value and the standard error of the statistic, that is what we call a margin of error. So some basic terminology here, relatively important, and I'm going to start showing you some graphics here in a little bit. So we're going to start with a sample statistic. So you're going to get some sort of sample. You're going to get either that sample's average or that sample's proportion. That is a statistic, okay? We're hoping our sample is a good estimate or guess on the population. The next thing we do is we're going to create an interval, because it's very unlikely my single sample is going to hit dead on to the population. So instead, what we're going to do is we're going to make an interval around that to try and say, hey, I believe my population is between here and there. So the things that are going to accomplish that is this thing called a critical value. It's a multiplier that makes the interval reasonably wide enough to have the stated capture rate. So a critical value is going to help create a interval that's beneficial to us, right? You guys just took a quiz. If I said, hey, yeah, the class average was between a 0 and 100%, you'd be like, great, that tells us nothing. So what we want is a reasonably wide interval. If I told you, hey, the class average is somewhere between an 80 and 85%, you'd be like, oh, okay, I kind of know what's going on. That's reasonably wide enough, okay? Then we have a thing called a standard error of the statistics. Some people call it standard deviation. What this is, it's going to reveal how accurately a sample of data represents the whole population. So you were used to some notation in the previous quiz, sigma p hat and sigma x bar. We're now looking at SE, standard error of p hat, standard error of x bar. You'll see that. And what we're going to create is we're going to create an interval that has a margin of error. So we're going to create the margin of error kind of really sets up how wide this is. It's a range of plausible values for the population parameter to be. I'm going to talk about this little graphic over here first, and then we'll talk about this confidence bit. So what's going to happen is you're going to have a point estimate. You grab a sample, you find that sample's average. That's what this tiny little dot does, okay? That's the first part of our equation that we're going to have. The first little tiny bit, that sets up the center of the interval. This back part, the margin of error, is both of these things combined. The margin of error is going to create how wide that interval is. So you're going to add a margin of error to come up with the upper end of your confidence interval, and you're going to subtract a margin of error to come up with the lower end. So you're going to be able to say, I believe my population's average, my population's proportion is somewhere between this low point and this high point. It is somewhere in there, okay? Now, how we state that in statistics is we talk about, hey, I'm 95% confident, I'm 90%, some sort of percent confidence in our interval. And understanding what that percent confidence means is really, really important. So when we say we have 95% confidence, what that's doing, it reflects our uncertainty in a sampling methods. So if I'm 95% confident, that's great, but I'm not 100% confident, so I do have some uncertainty in our sampling method. You know, what if I got one of those super, super, super rare samples that's all the way on the ends? Not going to happen often, but it can happen. So there is some uncertainty there. So what a 95% confident means is if you gather many, many samples and you construct many, many intervals, 95% of my intervals will capture the true population parameter, okay? So it's like if I go out, grab a sample, build an interval, different sample, build an interval, different sample, build an interval, 95% of those intervals will capture the true population proportion. So if I went back to that fishing analogy with throwing a net over a lake and trying to capture a fish, a 95% confidence in that would be if I go out there all day, I throw a net, see if I got a fish. Go somewhere else, throw a net, see if I got a fish. Throw a net, see if I caught a fish. The idea of 95% confidence is 95% of the time that I threw those nets out there, I caught the fish, which means some of the time I didn't, okay? Really quickly, I'm going to go through this. Don't want to make the video too long, but try and speed it up a little bit, and then I'll talk to you about, show you some visuals of what's going on. So there is on this top part, this is the general setup for confidence interval problems, and we have this acronym of PANIC. So anytime I'm going to make you do a confidence interval, we're panicking, okay? It's the general setup. The order is we're going to have a parameter first, then our assumptions, name the interval, then we're going to actually do the interval, and then some context to wrap it up. This packet, we're going to start with proportions first, you know, so things are like, oh my gosh, 77 out of 100 students love White Castle or something like that. That's a proportion, right? So here's the general setup and what it looks like. General setup of confidence intervals, panic. We're going to write down our parameters, establish context. Should make sense that you're like, oh my gosh, that's similar. Then your assumptions, make sure we're playing by the rules, name what we're doing, actually do some math, and then some context. These problems, not so bad. Here's what it specifically looks like for what we're going to be doing is one proportion z intervals. So we're going to get a sample proportion to try and predict an entire population. So prom's not too far away. Maybe I use a sample of Pattonville High School students and ask them like, hey, do you plan on going to prom? I get a proportion of that. Like, oh my goodness, 17 out of 30 students said they're going to prom. I'm going to use that sample to try and predict what the entire population of Pattonville students is going to do. So again, we're going to have our statistic plus or minus the critical value times the standard error. So this is my formula here. P hat plus or minus, it's called Z star, and we're going to multiply P hat times 1 minus P hat divided by N. From our sampling distribution stuff, this should look eerily familiar because it is, and you can kind of see a little bit of the loose connection to sampling distributions. What I kind of do to kind of reason through this is, since we don't know P, we don't know the population proportion, P hat is a good substitute. When you read through these problems, you're not going to be able to write down P equals some number. So if you don't have a number for P, use P hat as a good substitute. What we're going to do on these problems is, first step is P is we're going to define our population parameter in context. So we're going to define P is the population proportion of Pattonville High School students that want or are planning on going to prom. Next, we're going to do our assumptions. We're dealing with proportions. We're going to do randomization, 10%. Those should ring a bell. The third one, since we're dealing with proportions, is large counts. Now for sampling distributions, we did N times P and N times Q. Again, we're switching to N times P hat and N times Q hat. Again, the logic is if you don't have a numerical value for P, we can't use it. So P hat is a good substitute. The name of this is a 1 proportion Z interval for P. This is our formula. We're going to have P hat plus or minus Z star times the square root P hat 1 minus P hat over N. Z star are these values here. When I'm in class, again, I'll explain kind of what's going on with there. I don't want this video too horribly long. And then finally, wrap it up with context. We are blank % confident that the true population proportion of Pattonville High School students that are planning to go to prom is between blank and blank. Okay, I'm going to show you some different things here. I'm going to talk about as the sample size gets bigger, the interval gets smaller. I'm going to show you a couple of these things real quick. So let's see if I can get this in the screen. So here's what's going on. This is kind of a visualization of what confidence intervals are doing. So I don't actually know what P is, the population proportion. So I get to choose just for this visual. Let's say the population proportion is 66%. So 66 of Pattonville High School students are going to go to prom. I'm going to make a 95% confidence interval, and let's do a sample of, let's do 75 students. So here's what's going to happen. I'm going to click this button for sample. And what it did is it went out and it randomly selected 75 students, we'll say, for my sample. And it calculated the proportion that would go to prom. So in this mechanism to kind of show what's going on, it found for my confidence interval 0.76. So 76% of their sample reported yes. Now you see, my sample said 76%. My population is at 66%. But what we have is we have this plus or minus. That's the margin of error. So right now my sample hit at this dot at 76%, and we add and subtract 0.10. That's the margin of error saying, well, we could have been off, so it could be as high as this and as low as that, which I think this math is very interesting because it does hit there. And it's showing up as red because we missed. This interval does not contain my green line there. We did not capture the population proportion. So right now at the bottom, I've created one total interval. We've hit 0, and that's our percentage hit. I collect another sample. This sample was centered at 70.7%. The margin of error now produced an interval that goes up to this point right here, all the way down to this point way down here. If you'll notice, this green line, which is my true population percentage there, is inside of it. So this interval shows up black because it did a job well done. It captured that population proportion. So if I keep hitting here, any interval that shows up black, that means job well done. We have an interval that inside of it is this 66%. We created an interval that inside is 66%. So I keep kind of spamming here, and we're doing pretty darn good. And then eventually, I hit another red. This is one of those super rare samples that, hey, we followed the rules. We did what we were supposed to do, but just in the randomization of the world, we got a sample that missed. Okay. What I'm going to do is I'm going to start spamming this button that says sample 25. it's now going to speed up this process. It's going to create 25 different samples, 25 different intervals at the same time. So we start spamming here. And you'll see as I'm spamming it, some are showing up black, some are showing up red. So I have some intervals correctly capturing the population, and I have some showing up red, which means, hey, we just missed. So I'm going to keep spamming this for a while. And I'm a little bit frustrated because this isn't going where it's supposed to be doing. So I just passed. I've done 3,000 intervals so far. 3,422 intervals I've created so far. 3,196 of them so far correctly have this 66% inside, okay? So if I keep spamming this, what should happen, and it's taken a little bit of time to get there because we had a terrible start, is you'll see this percent hit is slowly getting bigger and bigger and bigger. What it's slowly going to climb to, oh, we just had a drop, bad run of luck, is if I keep sitting here and spamming this, and I mean, I'm going to have to sit here a while and spam it, this percent hit is going to slowly approach 95%. That's what a 95% interval means. It's saying that, hey, if you keep doing this process over and over and over, 95% of your intervals created will actually capture, man, we're going the wrong direction, will actually capture this population proportion here. So I'm going to have to sit here a while, and what we mean is you're going to have to make a lot of intervals. 8,000 is not enough. It's sitting here and you're just making intervals for days and days and days. And in an individual problem, we're going to create just one of these intervals. We will never know if my interval did its job or it's a red one and didn't do its job. We don't know. We don't know. You either did or you didn't, okay? But the hope is that our confidence is at 95%. Oh, dang it, I wasn't even paying attention. I hit the wrong button. So I reset here. And it's doing a little bit better job. We're floating closer to that 90. Oh, now we're dropping. Goodness me. Okay. The other thing I wanted to show you is these were samples that had a sample size of 75. The thing I want to show you is what happens as you increase your sample size. So when I do a sample size of, we'll do a sample of 500, see how my intervals got much, much smaller. So as you learn more information, your sample gets bigger, you learn more information about your population, we can make some very, very specific and smaller intervals. And as I sit here spamming, you'll see, I just passed 1,000 intervals created, getting close to 1,750, and there's 2,000. I'm sitting at a percent hit, 95.2%. So I've made over 2,000 intervals, 95.2% correctly captured this 66% inside of it. That's kind of what's going on with confidence intervals. I know it's a very, very lengthy video. It's a big, big topic that if anyone's like, hey, have you ever taken stats? Yeah, you need to know what kind of confidence intervals are. So long video. Once we start jumping into problems, this is going to make a little bit more sense.